Hello everyone, I'm Toshiyuki Shimizu. I am in charge of research and development of supercomputer systems. Today, I'll explain Fugaku's benchmark results, focusing on TOP500 and HPCG. This is the outline of my talk. First, I will introduce Fugaku's design goals and approaches briefly. Next, I'll review the benchmark results. Then I'll show Fugaku's specification and features. After that, I'll discuss the TOP500 and HPCG benchmarks. Let's get started. These are Fugaku's design targets and our approaches. As you know, Fugaku was designed and developed to maximize application performance, not to win benchmark rankings. We set our performance goals for application performance to 100 times greater than that of the K computer. Our co-design approach of working with application development teams was effective. Second target is power efficiency. We set the maximum power consumption of the system to 30 to 40 megawatts. To achieve superior power efficiency, we developed the CPU, Fujitsu A64FX, using cutting-edge silicon technology and our proven low power and high performance logic design. We also implemented power knobs to limit power consumption. Third target is usability. Fugaku is general-purpose CPU-based system with no accelerators. We supported the ARM ISA and ARM standard Linux distributions. These are key to broadening applications and offering the same usability that users are accustomed to with Linux environments. This slide shows the benchmark results of Fugaku. Fugaku is ranked number 1 by a large margin in 4 major performance benchmarks. These are Fugaku's score of ISC20 and SC20. Fugaku is the first machine ranked number 1 in all 4 benchmarks at the same time. I will show some history of benchmarks from K-computer generation. This graph summarizes champion machines in the history of TOP500 and their performance, normalized by K-computer performance in linear scale. While many of the flagship machines are rated number 1, Fugaku's performance gain is significant. This graph shows the history of the HPCG benchmark. The HPCG ranking started in June 2014, and only 4 machines are in first place. Tianhe took first place at the beginning. After that, K-computer took first place through benchmark tuning, even though K-computer is 3 generations older than Tianhe. Since then, Summit improved its performance, and then Fugaku demonstrated over 5-fold improvement. This graph shows the history of Graph 500 benchmark. There are 4 number 1 machines. K-computer and Sequoia were good rivals, improved their performance each other. K had kept first place for 9 consecutive terms since June 2015, 10 times in total. Sequoia and Sunway scores are very close. After retirement of K-Computer, Sunway won the award for the first time in November 2019. Then Fugaku made more than quadruple the Sunway's performance. In summary, K recorded number 1 on all 3 benchmarks, and Fugaku is the first machine to win all 3 benchmarks simultaneously. Here are the top 500 and HPCG benchmark results in last November. The graph on the left shows the top 500 and HPCG performances in order of top 500 ranks. Top 500 and HPCG are known as bookends. This means that many application performances are within the range of top 500 and HPCG performances. As you can see, Fugaku's HPCG performance is higher than the top 500's 20th place. The graph on the right shows the peak performance of the systems and HPCG and top 500 performance. These are the efficiency trends of both benchmarks. Fugaku showed good efficiency in both benchmarks. This slide summarizes Fugaku's node and system specifications. The Fugaku's computer node consists of a single A64FX CPU featuring ARMv8A instruction set architecture. The CPU runs at 2.2 GHz with 48 cores and SIMD width is 512 bits. It integrates 4 HBM2s, high bandwidth memory on the packages, and integrates TOF interconnect D on the CPU die. Fugaku system consists of more than 150,000 nodes, and the TOF-D topology size of 6-dimensional mesh torus is 24, 23, 24, and 232. The next 7 slides discuss the results and tuning of the top 500 benchmarks. This slide summarizes the top 500 parameters and performances of K-Computer and Fugaku. The HPL performances of K and Fugaku are 10.5 and 442 petaflops respectively. It is 42 times improvement, while the peak flops improvement is 47.6 times. We used hybrid parallel execution model, 4 processes per node and 12 threads per process. We ran the Green 500 in optimized RAM at CPU frequency of 2 GHz and 15.4 gigaflops per watt was obtained. Fugaku is 10th on the latest Green 500 list. The following slide discusses benchmark parameters N, PQ, NB, and performance tuning. Parameter N specifies the size of matrix. To improve the performance, N should be as large as possible. This parameter is discussed in the later slide. The parameters NB is the blocking factor. We used 320 for the benchmark. This number is set because it is the smallest number that provides the best DGEM performance. the number is smaller than k on other machines with 512-bit SIMD CPU. The parameters P and Q are used to configure row and column processes, respectively. These parameters change the communication pattern, message size, and computational density, which greatly affect the performance. These parameters should be carefully selected for communication and computational optimization. This will be discussed in the next few slides. Large N achieves higher performance and requires longer benchmark execution time. The graph on the left illustrates the HPL execution time and achievable efficiency on a full configuration of Fugaku system. This graph is plotted using the logs of the HPL round of TOP500. The iterations are arranged in reverse order from the last iteration, and the efficiency is calculated by dividing the cumulative number of operations up to each iteration by the cumulative execution time and plotted. The latest score using 21 million for matrix size n achieved an efficiency of 82%. 28 GB of memory was used. Since memory capacity of 4 HBM2 is 32 GB in total for CPU, 87% is used. The table on the right shows the breakdown of the execution time. 90% of execution time was used for DGEM. This slide shows the number and configuration of P and Q processes in a node. Fugaku's A64FX CPU has 48 cores. Hybrid parallelization of the threads and processes is recommended to utilize this large number of cores to improve performance and memory utilization. 4 processes times 12 threads configuration is recommended. In our column measure process mapping, the communication patterns for the P direction can be arranged to skew. Q direction communication occurs simultaneously in adjacent point-point processes. We chose 1/4 for the P and Q configuration in the node. In this configuration, each process can use the largest interconnector bandwidth. Since 4/1 configuration needs to share the interconnector bandwidth, effective bandwidth for each process is limited. This slide describes the P/Q configurations available in a full configuration of Fugaku. The Fugaku TOF-D size is physically configured as 24, 23, 24 with the mesh on the y-axis and the torus on the left. This table lists all possible P/Q configurations. Although P and Q communication generally occurs in different phases, HPL's look-ahead feature allows you to start the next phase before the current phase ends. In order to utilize TOF injection bandwidth as much as possible for each of P and Q direction communications, it is necessary to increase the number of axes constructed to each of P and Q and to carefully avoid congestion. Since TOF-D supports 6 DNIs or DMA engines, up to 6 simultaneous communications can be utilized. In addition, P direction is preferred to be a cube because its communication patterns include collective communications. As a result, these three combinations are candidates. The computational performance in the HPA run of three combinations of P and Q was evaluated. The graph on the left plots the average performance of DGM routines of a process with 12 threads using 8.3 million for n. The results show that smaller P over Q results in higher performance. To estimate the HPL performance, we sampled the performance in the range of 1,675 and to 26,000 iterations in the HPA running of the full configuration of Fugaku. The matrix size n is chosen to emulate each part of the HPL execution. 21 million for the beginning, 15 million for the middle, and 8.3 million for the ending. Then, the performance prediction of HPA runs are estimated. This assessment also reflects the communication effects more realistically. As a result, 864 by 736 is expected to achieve the best performance. The final tuning point is the communication function. This shows the HPL execution steps. The calculations and communication at each step are shown. Blue names are calculation libraries and red names are communication functions. P direction pivot pivots a column using MPI send and I receive. P direction swap calls bcast and altogether V MPI functions. Effective bandwidth of these functions is very high because they are optimized to TOP500 using multiple TNIs and TOP500 axis. Q direction bcast is implemented by MPI non-blocking I-send and I-receive functions to allow overlap with matrix multiplication. In dual-ring pipelined broadcasting using two TNIs, the maximum hop count is 92 when Q is 736. In order to utilize all bandwidth of TOP500 links, one process in a node controls inter-node and intra-node communication. Shown here are the power consumption logs and computational performance from the top 500 benchmarks performed in Fugaku last November. The power consumption pattern is very close to the computational performance. These gray patterns are logs of the Green 500 optimized run. The only difference is the CPU frequency of the top 500 and Green 500. The next three slides describe the HPCG benchmark results and tuning. This slide summarizes the HPCG parameters and performance of K-computer and Fugaku. You can see that HPCG performance of K and Fugaku are 0.6 and 16 petaflops respectively. It is 26 times performance improvement, while the memory bandwidth improvement is 31. We use hybrid parallel execution model since thread parallelism is increased by a factor of 3 compared with K-computer. 2 more iterations are required. I will discuss for the benchmark performance tuning on the next slide. The graph on the right is log plot of peak and HPCG performances. In addition to the data from TOP500 in last November, K-computer results from ISC16 and SC16, Fugaku results of ISC20, and an internal measurement of 83,000 nodes were added. The table on the left shows the Fugaku's HPCG performance and efficiency. Fugaku has shown excellent scalability with increasing number of nodes. TOFU interconnect decommunication functions such as hardware reduce and 6-dimensional simultaneous communications performed well. In addition, the results of last November shows a further performance improvement due to the fine-tuning for a wide SIMD CPU. I will introduce example of our tuning in the next slide. This code is simplified representation of the symmetric Gauss-Seidel loop. The innermost loop is SIMDized and utilizes gather rows. Typical loop count is about 27. These optimizations shorten the interval between the store of sum to the array xv on the line 10 and the load of xv array at the next iteration on the line 7. If the load is issued and the store is still in the store queue, the load for the same address is retried or delayed. This is the called as store fetch interlock or SFI, and it limits the performance. A64FX supports the SFB store fetch bypass, which forwards data to avoid retrying load instruction. However, the Scala store followed by the gather load is not supported. To relax the interlock, we introduced a variable that holds the sum until the next iteration ends, and then stores the sum in the array xv. Let me summarize my presentation. The supercomputer Fugaku achieved excellent results in the benchmarks. Fugaku's design goals are to provide 100 times the performance of the K-computer in real-world applications and to support a wide range of applications. On the other hand, benchmarks are designed to evaluate the performance of supercomputers in some specific aspects of real applications. Fugaku is expected to perform well on many benchmarks. K-computer was used as a machine with good balance for 8 years and produced many valuable results. Fugaku is a successor of the K-computer. Fugaku's benchmark results are promising for design goal of application performance. Fugaku's design goal of usability is going to be evaluated by many users, and that will bring more valuable results. So let's use Fugaku to prove it. Thank you.